presentation. Exterior insulation, now I have to behave myself. Notice the little red line that showed up on the outside of the insulation. This is not a code requirement. This is a really nice to have. And I'm not saying 2 lines of air tightness. I'm saying let's make sure our insulation is installed in a good manner, right? We don't want big gaps and cracks in our insulation. So tight fitting mineral wool, spray foam, board stock that's sealed or taped or both. But we want to avoid large gaps getting behind our insulation. So for the purpose of this though, we're going to say we got 1 line of defense for that air tightness, dedicated plane that we can clearly transition to. The other part about that air barrier being on the inside of the insulation, we want to keep that money that we spent air conditioning or heating the inside of our environment on that conditioned side of the insulation. If we start putting our air barrier on outboard of the insulation or halfway between, which sometimes can work, that conditioned air can work its way in and out of that insulation. And so you can't capture that kind of stuff in an energy model. But we know the reality is it's affecting the efficiency of our enclosure or our building systems when you can pump that air in and out of the insulation. So again, we like to keep the air barrier on the conditioned side of the insulation whenever possible. Lastly, vapor. Again, I'm not going to focus in on this from a diffusion standpoint. There's enough discussion out there as it is. We're going to focus in on from an air tightness standpoint. So where we have our air tightness plane, we're stopping a lot of vapor flow by means of air path. And that's where we're going to really focus that in when we're talking about humidified buildings. So we're going to do the same thing with the roof. We're going to go much faster though, because now you get the concept, right? And we're going to have one roof that we're going to look at. It's a traditional commercial flat roof. Lots of different components in there. Do the same process. In this case, we don't have redundancy from a water tightness standpoint. We have an exposed membrane roof on the top. That's where most of our water tightness is going to come from. From an air tightness standpoint, similar to the wall, I like to suggest that we put it on the interior side of that insulation. Again, keep that inside the building, conditioned inside the building. Don't let it permeate back out through the insulation. Now, it'd be nice if that's a dedicated membrane, and there's lots of options for that. There are other ways to do that, but again, let's focus on the fact that we have it down underneath at the deck level. Continuous insulation is obviously pretty straightforward with commercial roofing products. We're typically above the deck. Again, if we can get that above the air barrier, we're on that conditioned side of the building and continuing that mantra where our air tightness plane isn't having to go through nearly the amount of stress that it has to go through. We will touch on the idea of the roof membrane being the air barrier and some of the pros and cons of that. So we're going to get further into that down into this presentation. So I won't touch on it right now. Most of the first part of the presentation is going to focus on that plane being down at the deck level. And then lastly, from a vapor tightness standpoint, with commercial low slope roofs, if you have an air barrier at the deck level and it's a dedicated product, 9 times out of 10, it's also going to be a vapor retarder. It's likely going to be self-adhered rubberized asphalt, a built-up roof, a mod bit roof. All those things technically from a diffusion standpoint are vapor retarders. There are products on the market that are getting introduced into this, but it does take time because from a commercial standpoint, 9 times out of 10, I need to have a tested assembly. It needs to be UL rated or FM approved or something. And many of the manufacturers don't have a material to be placed at that level that have been tested yet that will actually be a permeable membrane. There are some that are working on it, some that are getting some success and traction on that, which is great. But most of them right now, currently, it's going to likely be a vapor retarder. And again, primarily, we're trying to stop the airflow that might have moisture in it. So I'm going to be less concerned about permeability. There are other people you can talk to about that at a later date, or maybe later this afternoon. Anyways, fenestration, moving on into that. We're going to focus solely on curtain walls. We're not going to talk about windows today. We're not going to talk about storefronts today. Focusing specifically on a curtain wall. And even to narrow our focus more, we're going to talk about your traditional stick-built pressure glazed curtain wall. Nothing fancy, not unitized, none of that stuff. Just let's keep it focused so we can hone in on how to handle this approach. And so if we take that, dive into the installation instructions of whatever fenestration product you're using. We love using Conair as an example. They've got some great installation instructions. Oldcastle has great ones too. Wausau does too. YKK, you name the manufacturer. Many of them have good installation instructions. This is an example of it. And the point of this is most of these types of systems from the glazing pocket back is not really sealed. So if we consider this the glazing pocket right here, all of this back here is not sealed to each other. Most of that is just dry fit. And that's important to understand. Connery also goes so far as to say on the left is the required primary seal. We call that at the shoulder of the mullion. On the right, there's an exterior weather seal and rain screen seal, essentially. And then they go so far as to say there's this optional cosmetic seal on the inside. They do not require this. They don't test with it. They could care less if it's there. So a lot of times we see with curtain wall construction, people are relying on that to try and make their transitions from an air and water tightness standpoint. And the reality is it doesn't do that much for you. If you're relying on that, you actually have to take several more steps. And Conair will tell you, you still can't eliminate the other two, or one, depending on which system you might be using. So if we break that down, same thing. We've learned a long time ago, we got two lines of defense with our curtain wall systems as well. They shed bulk water on the outside, but we've learned well before my time that windows leak. So let's build internal guttering systems in them to collect that water, drain it back out. So we got our two lines of defense. From an airtightness standpoint, the fact that we're weeping that hole out and draining that water says it's not airtight on the outside. So our airtightness is at that primary line of sealant with all the gaskets and internal seals that you have with the curtain wall. From a thermal standpoint, pretty straightforward. It's the insulated glazing units, the gaskets, the thermal brakes, all that contributes to the thermal performance. And then lastly, from a vapor standpoint, if you're airtight in this situation, most of these materials are vapor tight as well. So gonna align right up with the airtightness layer. So why does all this matter? Obviously, we have to have an effective separation from inside to outside to make sure we don't have problems. They have to be continuous to be effective. Some obvious statements here. And if we have our discontinuities, where do they occur? This is just the short list of where discontinuities can occur. They can be any number of other issues. And what do they cause and affect here? Some basic stuff, certainly water leakage. And really, this is just our 4 control layers listed out in a different way, right? We don't have water control. We might not have air control. We'll have poor thermal bridging, which relates to poor energy performance from all of those things building up, which also could result in condensation. And then you take that list on the left and apply it to what the results will be on the right. These are just the things that'll happen. This is what it's going to cause. Bugs, mold, rot, corrosion, reversion, all those great things. Things we want to avoid. So Laverne touched on this a little bit. I'll go a little bit quicker through it. Obviously, climate zone matters from an energy standpoint, but we learned rather quickly that moisture migration is going to be much more significant. Old study here, this is not new. It's basically just saying that even if you're code compliant and then reach from a whole building air leakage standpoint, going up to something that the core might require or down to what the core might require, and then go even further maybe in the passive house levels, how much air tightness is going to save from an energy standpoint. And it does generally matter throughout all climate zones. It's going to matter further into the colder climates. It makes sense. But how much does it really matter? That's where that calculator came in that Laverne talked about. I'm going to show my slides as well, just to re-emphasize, go use it, go check it out, give us some feedback on it. I'll give credit where credit's due. Joe Stiebrick, Building Science, great graphic. I couldn't even possibly try and say something better. Here's the bottom line, 100 times more water is going through that tiny little hole versus diffusion, right? So that's why this is so important. Not going to dwell on it. We took those things, combined them, because we got feedback from the industry saying, great from an energy standpoint, but what's more important is the water tightness and how much vapor flow is going through that air leakage. Laverne's examples were way more extreme than mine. Mine is just showing you that we have all these locations all over the country. We have, I think, 12 different building types you can look at. And this was just one example. What I want to re-emphasize, though, originally this was used for retrofitting buildings, really the sales point of retrofitting buildings. So we know they're very leaky. So if we go take this calculator to an owner and say, this is how bad it's performing as an existing building, if you go put an air barrier in it, we can make it perform so much better. And just comparing it to code, and I don't know if Laverne touched on it, but if you start with code and go down from there, there definitely is a diminishing returns. Because as you get tighter and tighter, you're going to lose how much more value you can get out of that from an energy standpoint, but not necessarily from a moisture standpoint. So let's keep that in mind. But go try it out. You've seen these with Laverne, so I'm not going to walk through it as deep. But it is a great tool that we'd love additional feedback on. Results of this, though, more graphical. What you're going to see in this next series of slides is what might be thought of as water leaks. As I say, water tightness is so important, right? The reality is this was condensation. This was the result of condensation. These are not water leaks. This is rot of wood due to condensation, poorly placed materials or missing materials. Condensation, not a water leak. More importantly to think about this, so those were cold climate type of situations that condensation occurred, but it doesn't have to be cold climate. This is in a middle south climate. And just an example of what can happen, we had an issue balancing this building from a mechanical standpoint, and you can see, so we went out and did some investigation. You can see there's perforated panels at that soffit condition, so you're going to automatically assume that this roof is probably a ventilated attic. You'd like to hope so, right? Because you got soffit vents everywhere. You go up into that soffit, and again, nothing wrong with this material. Technically, it's a water-resistant barrier. And since it's a ventilated attic, probably not a big deal that you have these holes and not sealed off real well. Not at risk if you're ventilated. And these are not small holes, and there's lots of them. So hopefully we're dealing with a ventilated attic. Because when you turn the other way, the water-resistant barrier just disappears, and there's not anything really sealed up when you go that direction. Turn your head the last direction, you can literally crawl into the attic from the outside through the soffit. And again, if this is a ventilated attic, no big deal. But what we found real quick when we did stick our head through that hole is a whole lot of ceiling tiles that we could see. Ceiling tiles are not airtight. And all the mechanical equipment, you know, it's nice that it was inside the building, but all that hot, humid air was dumping into the non-ventilated, I guess it technically was ventilated, but not the way you'd want it to be. And it actually wasn't condensing on the ductwork, it was condensing on all the supports for the ductwork because they're not insulated and dripping down onto the ceiling. And then the entire building looked like that throughout, all because of a roof to wall transition that was not airtight and designed poorly from day one. It wasn't an installation issue, it just wasn't designed correctly from day one. So we're not going to talk about steep slope roof today because they get a little bit more complicated, but the common parapet, same kind of thing happens. This is what you traditionally see from decades ago. A water-resistant barrier of some sort behind a veneer, and then a parapet with the roof membrane flapping over the top, waving to you as you drive by on the highway, right? No connection between them. And that is a direct path for airflow to get in and out of our buildings. And notice I said in and out, not just out. It can bring contaminants in as well. You guys are experiencing that with smoke, right? We want our buildings to be airtight so we're not having to deal with trying to only rely on our mechanical systems to filter out that smoke. The building needs to do its part as well. Other areas with an interior vapor retarder, trying to make that connection, even if I have the air and vapor barrier and I have an air and vapor barrier at the deck, how do I connect the two? That's not easy to do. Decks are not necessarily airtight. I'm here to tell you, roof decks, almost every kind, if not all kinds, are not airtight. We need to make them airtight. And then look at that perimeter beam. Many of our perimeter beams are nice and tight to our exterior walls. There's not a lot of room to work up there and do anything and do it well. So relying on interior vapor retarders in this type of application, it's really challenging to get that continuity to occur. And in my climate, and maybe some of yours, when that happens, it turns into ice. It's not just flow issue. So it's not just an energy issue. It's not just moisture traveling through. This is when the moisture travels through and hits the dew point and starts condensing and then freezing. Then the old joke is springtime comes, it all melts, and the roofer gets a call because the roof must be leaking, right? No, it's the building was leaking. We use infrared. Laverne touched on this as well. Many of us will touch on this to identify these things, whether they're in an existing building or new construction, certainly. And I want to touch on another example of where a contractor attempted to try and fix this interior connection. And this is not by any means an attack on the contractor. They did their best to try and make this happen with a very difficult situation. So they recognized how challenging it was going to be. So they went ahead and pre-installed the interior air and vapor barrier on this because they knew they wouldn't be able to get up there in the future. And the reason why is because of that perimeter beam. It was literally inches away from the wall. And it was, I think, 3 feet tall. So trying to get in there to actually do anything, they pre-installed it. It was a very logical move. If we move up to the top, you can see how it's coming up and around that roof deck. Now you see a platform frame parapet. How do you get from the platform frame parapet to the air vapor barrier that you see on the roof deck, the black stuff on the left? Another challenge, they had to go underneath that roof parapet construction. Once they got underneath, they needed to connect to that stainless steel flashing that you see there that's connected to the air barrier. And how they did that is in this next photo, underneath the parapet wall, underneath that flashing, all taped together. And I'm seeing lots of faces saying, how in the heck, right? That's the reality. How in the heck do you do that? And it's extremely difficult to go from inside to outside back to inside. So this is not proposing that we should do this. This is actually showing why we shouldn't try and do this. Other conditions that are notoriously problematic for us, and I do think we as architects can do better at this as well, this perpendicular wall parapet to an adjacent high wall. This is a notorious place for air leakage to occur. Again, we can use infrared technology to kind of highlight it, but quite frankly, you can walk around on a cold day and just feel the heat blasting out of that like a hairdryer. I mean, it is that extreme because the wall is so airtight and the roof is so airtight. Here's our little orifice. It's just blowing all kinds of air out of that because that's the only place it can escape. So we can use infrared to identify it and try and make things better. Here's another example of the same thing, and this one was much worse. You can see the amount of energy being lost out of that one little detail. That one spot is significant. We have the best walls, the best roofs, and this little miss right here is letting all the energy that we created inside our building out. Here's the after effects after it was repaired, so you can see the significant difference in performance and see how critical it is to get this stuff done and done right. Manufacturers have done a great job detailing this for us. I think from an architecture standpoint, we need to take that first step as well because we might get the same manufacturer on the roof and the wall, but it's pretty rare that that happens all the time. So here's an example of where we had mismatched manufacturers, where we had that low roof, that low parapet slamming in perpendicular to a higher wall, and how we might address it. And this has got nothing to do with the two manufacturers. The one thing to note here is the compatibility of these two may not be perfect. It might be, but it might not be. And I will tell you from a long-term standpoint, what we start doing is introducing termination bars. And this is at the air barrier level to make sure that if there are any potential issues that might occur over time, you're still being locked down with a mechanical attachment at that air tightness plane. So keep that in mind for projects especially if you're dealing with different manufacturers and different material technologies. Back to the fenestration side now a little bit. Again, not a water leak. This is condensation and not necessarily in a very cold environment. This actually was in Virginia, all due to condensation from an air leak. The transition between the window and the wall was not airtight. All the cold outside air bypassed that thermal break of the curtain wall system, cooled the backside of it down, and caused condensation. And this was actually in a relatively low humidified building. It was an archive library. Worse, as you get colder climates, that water turns to frost, and notice that the sill is not condensing, the jamb is. The sill had a nice airtight transition, the jamb had no transition. It was just inside to outside. And that's how critical this stuff is, because it gets even worse when it gets colder, it just starts building up, and then again, melts. And this is not great when it's in medical facilities either. Keep that in mind. So how do we avoid it? Since we're all architects, like I said, I have a license to pick on ourselves. One thing, we could just have square little boxes, make things easier, but we don't do that. We put every type of curtain wall, every type of storefront, every type of window, every type of roof, all on the same job, possibly in 30 different sections on that job. There's lots of ins and outs, right? So there's a lot of different avenues and possibilities for this discontinuity to achieve. So if you rewind all the way back to understanding the system, you need to understand every one of those systems and where those transitions need to occur before you can ever start connecting the dots between them. And the more different materials we start using on our products, the more different systems we use on our projects, the more complex that gets. And the one thing to start thinking about is, do we really need to use a curtain wall and a storefront and a window? Can we do it all with one type of system? Do we really need to do this type of rain screen, this type of precast, this type of something else on the walls? Can we do all rain screens and keep the transition details essentially the same, just changing up the claddings? Keep all the windows the same, so that your transitions will ultimately be equal to each other at every one of those locations. So we have this little other game that we play. It's called Trace the Layers. You guys probably have heard some version of this, and it goes back well before I got into this industry. Literally take your pencil and highlight where the plane of water tightness is on the roof. You go up over the parapet, and when you connect to the wall, if you have to lift your pencil and put it back down, there's a discontinuity. keep going down through the wall, you get onto the curtain wall. If you can keep on going without lifting that pencil, now we use a mouse or a stylus or whatever else, without having to lift it, now you don't have a discontinuity. Anytime you have to stop, lift up, and move, you got to zoom in and figure out how you're going to address that discontinuity. And the key part of this is this is not a new thing. Maybe the new mantra wants to be thought about is that was airtight or water tightness. You need to do the same thing for air tightness, the same thing for thermal tightness, and the same thing for vapor tightness. And then as Laverne had mentioned, don't forget about the bottom. There's 6 sides to this box. We got to trace that line around and make sure we're accomplishing it everywhere if it's necessary, not always necessary. So with that, diving in now into the transitions themselves, with that being as our table set, we're going to look at roof to wall, we're going to look at window to wall. We're going to start with roof to wall. We're going to look at primarily the air and vapor tightness, not diffusion, but the air and vapor tightness, how we're controlling vapor by means of airflow. We will look, and we have to make the assumption that the rest of this is watertight and the thermal performance is generally considered. So we're really going to now focus in on the air and vapor tightness of this transition. We're going to look at 3 different types. We're going to look at platform frame, or I'm sorry, platform frame on the left, steel stud construction, balloon frame in the middle, and then CMU platform frame as well on the right. And we'll expand on some of the benefits and risks of each one of these. Starting with platform frame, we'll spend the most amount of time on this. If we at least on our documents, and this is becoming more and more codified, that is required to clearly show where the plane of air tightness is as it goes from all the way around the building, quite frankly, but specifically at the parapet. We need to make really bold lines that say, this is where my air barrier is, and this is how I'm getting it connected from one to the other. I'm a big proponent, if we're in this digital world, we could probably actually use colors if we want, make it even easier for everybody. So to the young folks out there, let's keep trying to push that down the road and make it even easier and better for us to identify. So step 1, we need to draw that line, make sure we understand where that line is. Now step 2 is how do we actually make that line? So if we strip everything back down to the structure and start building the layers back, we got options. You know, the roof air and vapor retarder could go installed first, and the wall air and vapor retarder could be installed second and lap over top of it. Mind you, this is not water tightness. This is just the air tightness plane. That's one option. We can do, and then everything magically gets installed around it. Option 2 though, or B, depending on how you read that letter, we strip everything back down. As you might guess, the wall barrier might go on first. The roof air and vapor barrier goes on second, laps over top of the wall. So that's one way we can do it. Second way, then everything magically gets installed around it. Option C, strip it back down to the structure again. Now it could be roof goes first or wall goes first and roof goes second, either way, but you don't actually connect them. So this is the second joke. The first one wasn't very good, so maybe the first joke. Who goes third here? How do I connect that dot? Some transition. Who? Sam. So you're thinking products. I'm just thinking more generically. Remember that company Laverne talked about? That's who goes third by others. Who's got it, right? That's the big question mark. Who's installing that piece? So there's lots of different advantages and disadvantages of each one of these things. We'll talk about a few of them. Primarily, in my mind, sequencing, compatibility of materials, and long-term adhesion. So similar to that term bar that I just talked about, thinking about that from who goes first, who goes second, or if there's a third individual, but maybe that third individual is actually one of those other 2 individuals. Kind of complex, right? Bottom line, from a sequencing standpoint, one thing to think about is, you know, this is an example of a standard roof system where the air and water barriers or air and vapor barriers coming up out of the parapet will lap over and touch the air water barrier on the wall, which looks relatively okay from here. 2 different manufacturers though. Are they compatible? Will they talk to each other? No offense, manufacturers, we love you, but you got to talk to your roofing companies as well. We need letters that say they're compatible. And the reality is they may not be. And so if I said in my design, I wanted this one, but the problem we have as architects that other people also need to appreciate, most of our jobs have to list at least 3 products in both specs, in the roof and in the wall. We can't possibly control that all of those interactions are going to be compatible. It's virtually impossible for us to control that. because you might pick manufacturer A on the roof and manufacturer B on the wall, and those two are not compatible, which may drive you to have to flip it the other way. Maybe they're compatible the other direction. So there's just, some might be peel and sticks, some might be fluid applies. Do those react with each other? We can get the answers. The point is we got to ask the questions and make sure we apply that appropriately. And a lot of that happens during the submittal phase, happens during pre-construction meetings, which is critical for that pre-construction meeting. That might happen before submittals start coming in, so that we can help inform that information. The reality with this is, you know, with some of the self-adhered membranes, if we look a little bit closer, sometimes, again, not a material problem. This is an installation problem. And then if we look even closer yet, we can stick your hand inside the building in some of these conditions. So we've got to do better and more inspections to make sure this stuff isn't happening, because it has nothing to do with the products. It's got totally to do with the application of them. So a note with peel and sticks, especially against fluid applies, and that's where that termination bar kind of comes in. Construction sites are dirty, they're dusty. It is sometimes challenging to get this to work, even in the best of situations. So having that termination bar to lock it down, you don't have that problem near as much if you use fluid applied transition materials. So something else to think about from which one you prefer. So which one do you use? I actually like to open this up to you guys. Do you guys have thoughts on this? There's benefits and risks of both, and I could talk about that for 30 minutes. We won't, but we could. But do you guys have any thoughts on this? Option C, okay. Excellent. So option C, because of better sequencing flexibility and likelihood of better compatibility on the products. Yes. That can handle both of them. Yes. Good qualifier. And we'll get back to that qualifier. Excellent point. So option A, because there's fewer products and there's more protection. I'll hit on that, and actually all of these kind of things together. I'm actually open to almost all of them. And I'd like to talk with the contractors to figure out which one they think will suit them best for their sequencing as well. Because sometimes we have the situation where the contractors want to get that air and vapor barrier down on the roof as a temporary roof. And the walls aren't even there yet. Right? So we can't do that flap that one way. I might still be able to do option C though. I got other situations, panelized construction is huge out here, right? Or across the country, it's gaining more and more traction. The wall might go up before the roof air vapor barrier is ever there, and it may want to flap over and be installed first. So there's a lot of sequencing that can happen. And I've actually had projects where over here on this part of the job, we did it one way, over here we did it another way because of project-specific criteria that happened as the project was being developed during construction. So it's really about being flexible and making sure that we're addressing it. The one nice thing about option 1A that I've heard versus 1B is if I get the roof side installed first, I can protect that wall to some degree from the backside. If I install the wall side first and the roof is exposed, I can put a lot of damage to the backside of that wall from a rain standpoint. So there is benefits to both. They all can be, all the risk for every one of those can be managed though. I like the option C because you're right, it separates the two materials totally. And I can hopefully find a material that's compatible with both. The flip side of that is now I got two different compatibilities I might need to check versus just one. So again, there's benefits and risks to every one of them. The key now that I'll take back to that big fat red dashed line that we should show in our drawings, we should actually show one of these. We need to do something. The biggest critique I get from this is contractors say, you didn't give me any scope to give out. Give me somebody that I can at least say it's theirs. Then you can have all the discussions later and shift scope back and forth, but give me something that I can price. If I just do the line, what do they do? You're leaving it totally up to the whim. So if you have a preference, put something in the drawings. Then lastly, the termination bar again, especially on self-adhered membranes. I say termination bar, it could be any number of things. It could be the buck for the coping. It could be the coping itself. There could be cleats installed that maybe could function as a term bar. My preference is just do a dedicated term bar, but there are other materials out there that could also function. The trim for the cladding system could function as this as well. The benefit of doing the termination bar is it's installed on day one, not waiting for the other stuff to come on. A couple examples of actually those same two manufacturers playing nicely together with a term bar so that if they don't play nicely together later, we've got it under control. Absolutely. So how can the specifications help with getting that stuff earlier or making sure it's at least happening? As soon as suitably possible, yeah. Not later, because far too often we'll find out that they may not be compatible after they've maybe installed or even just submitted and wasting everybody's time reviewing submittals. So it should be one of the first things that gets submitted to the team. And quite frankly, the architect shouldn't even get it, make sure the contractors are doing that stuff because they might find out ahead of time it's not compatible. We shouldn't be the ones having to find that out firsthand. That should be a first check at the contracting level. And I'll get back to you, but yeah. I sense that you might have something to say about that exact topic. Yes. That helps force the issue, but to her point, it needs to be done sooner than that yet, hopefully, but at least the mock-up, requiring the mock-ups and the specs might uncover the fact that that stuff didn't happen when it should have. No, I know, but it should be one of the first submittals. It should come with the system submittal. You know, I don't want to even see shop drawings. Send me the system and then show me that you're compatible with your adjacents. Now, what we have in the ABAA spec, and what it shouldn't just lie in the air barrier spec. When we talk about ABAA is more than just the wall air barrier, we're related to the roof, we're related to the windows and the sealants. I suggest that we take the same language that we have in the ABAA spec that says, give me that compatibility letter. It may not be the job of these people back here. It might actually be the job of the roofing manufacturer. It might be the job of the sealant manufacturer. So that same language really wants to be connected throughout all the different specs to hope, I hate to say hope, but hope it's going to get covered faster and not just left to the air barrier manufacturer, because it's not just their responsibility.
Well, if you hold a pre-construction meeting and you're going through the details, those decisions about A, B, or C can be handled at the pre-con.
Yep.
Saying, hey, we may need the detail may show option A, but
we need to switch.
We may want to do option B. It gets handled at the pre-con, and everybody gets an agreement, buys in.
Yep. And at that point, if there's a switch, we need immediately that letter that says it's okay. And hopefully they might actually come prepared with that letter to say to the architect, we've already checked. This will actually work better. So these are. Yep. I will definitely agree with at least one, maybe two. I could not suggest that the architect could possibly check all iterations of the ways it could be, but we do need to at least make sure we have one that will work. If we set up for failure by the design, I agree that that's not appropriate either. So, all right, talking about this from a condensation standpoint and a thermal standpoint, you know, we have this big red dash line going up and over, but like I said, the metal decks, the roof decks, that's not necessarily concrete. They're not airtight. There's definite avenues to get up into parapets. We like our nice tall parapets so we don't have to put guardrails on our roofs. Some people like really tall parapets because they like to hide all the mechanical stuff that should have been in a penthouse in the first place, but we couldn't afford to move the roof up another level, whatever the reasons are. But we can get air way up there. And when you get air way up there, it's cold up there. We're not heating that space, right? And if that air has moisture in it, condensation could occur if it's typically in the humidified type buildings again. So if we have that interior humidified building, this is where the contractors like to kick me off the podium. Cut off the airflow at the deck level, get it out to the outside of the air, and make that, build your structure on top of it, and make that connection here, down low. So you're not letting the air get up into the parapet in the first place. It is got more sequencing issues. It's got more issues altogether. When you're dealing with humidified buildings, there's more issues to deal with. That's the bottom line. You can't treat them like the normal building. Maybe it's a third piece again that you install first that the other two pieces can connect to later. But it certainly needs to be addressed, and quite frankly, get rid of the parapet altogether is the easy answer, but we don't like doing that either. And then insulate in that stud. If it is a stud space, insulate it so it's keeping that air and vapor retarder connection warm, keeping condensation away from that level. All right, moving on to steel stud, balloon frame construction, same kind of concepts. We're not going to go through the who said goes first, second, third, who's on second, all that stuff. But we will jump right to that condensation concern. Now we have a direct path going up into that. There's not even a deck that might kind of sort of impede stuff. It's very easy up into that parapet for, again, moisture laden air. So if we have to, we got to find ways to plug that hole. I'm going to warn you, plugging this hole is not an easy task to do. There's lots of little holes that are hard to find that can bypass this. So fire rated joints could be a great option for this. Spray foam could be an option for this. Potentially, depending on some of the fire restrictions you might have. You might have to have a fire rated joint anyways. Might be a rated deck that has to have that regardless. And you know, we want to get that into that stud space, fill that from inside to outside. And that's where the big challenges actually occur. Everything else gets installed around it. We fill the stud with insulation as well. But here's the big warning. If anybody's been on the site looking at fire rated joints recently, and it's not a recent thing, this has been going on forever. Looks great from afar. Underneath that, there's all that mineral wool. There's all kinds of little nooks and crannies that we're trying to seal around. The mineral wool is not the air tightness layer, it's the spray applied material. But the studs have those intricate shapes. Sometimes they're stacked next to each other. Sometimes we have structure that goes up into there and they create more intricate shapes that have to be sealed around. Fire rated joints need better inspection maybe. I mean, we see this a lot. That little tear, that's an air leak all of a sudden. If you got a ventilated parapet or a ventilated overhang and this is what you're relying on, you need to make sure it's done and done really well. It doesn't take rocket science to know that something like this is not airtight. So if we're relying on that, we really need inspections to make sure. And who's inspecting this stuff? Fire inspectors? Are they inspecting every inch of it? Are you inspecting it? I'm not inspecting it, but we need to, if this is what we're going to rely on for that air tightness line. Big other problem as architects, it's not a problem for us. We have to do this. We delegate the design of the cold form metal framing almost all the time, right? So we don't have a lot of control of what that framing is. There's often times where we have double, triple gang studs back to back to back for the structural purposes. So sometimes can be back-to-back studs, or they can make little donut shapes, which create little chases up into our parapets. And they have holes in them as they go. So they got great inlets and outlets. And we can see this with smoke. We just right into that stud space, going up into the parapet and outside the building. So again, if we're relying on fire-rated joints, all these holes have to be plugged. And there's a lot of those little holes that hide around our parapets. So whether it's fire-rated joint or spray foam, all of that stuff needs to be addressed. And that's the big warning. Be careful using that and make sure that somebody's checking up on it. Moving on to CMU real quick. Same as the platform frame, essentially, conversation. That big dashed line going around. But again, from a humidified standpoint, this works fine. Non-humidified, no big deal. Cold climate, humidified. That moisture can get up there, cause problems. Same idea. We need to find a way to choke it off underneath the masonry, which just causes shivers down some people's backs, especially structural engineers. Certain structural engineers will tell you that it doesn't matter because when the wind blows and pushes on that parapet, it's going to break that bond anyways, and you don't necessarily need a bond. Kind of got to decide that as your own project team. Most of the strength there is coming from the connection through the reinforcement. If your structural engineer will let you do this, you could also, again, look at using a different material to dye in there so you can avoid some of the sequencing issues. If it's still a problem, don't use a CMU block wall as a parapet, go back to something else. All right, roof with no air barrier, dedicated air barrier. The dedicated air barrier has been eliminated because this is our favorite VE item in the roofing world, apparently, from my experience. Don't worry about it. We'll use the roof membrane as the air barrier. Okay, great. Maybe in some climates, but mostly not a good idea in most. So first thing to recognize with that is now we don't have that big red dashed line anymore. We got to find a way to get the roof to the red line, or the red line to the roof, or a third piece in the middle again. Somehow we got to make that connection happen. Again, there's lots of options for that. It's just recognizing to do it in our drawings, and then we also have to make sure it's happening in the field. A lot of the roof manufacturers do not have standard details that address this, because inherently they don't typically use their roofs as air barriers. If you want an air barrier, you're better off putting it down at the bottom of the deck. Doesn't mean that it can't be done, but maybe we shouldn't do it. The other problem with this is now from a humidity standpoint, we're going way out into that parapet. We're not even protected by the box anymore. And it can get much more severe. And we can do all the plug and pray methods that we have to fill that parapet up as best we can and stop the airflow. But the reality is the airflow just goes around it, because our metal deck no longer has an air tightness plane on it. Metal deck has holes in it everywhere. The insulation is not airtight. It just goes right through the roof, gets into the parapet, possibly going into the roof, causing other problems. Yes.
At least in the area where we work, more common to have not have insulation on the interior face of the parapet wall and rather have the interior.
Yep.
Which makes the vapor barrier stop the high insulation. So at that roof insulation, you also have an air break depending on how your sheet is treated that covers the transition. So during air testing,
Ballooning up. Yep. So the comment was, there's oftentimes not the insulation on the backside and you're going membrane directly to the sheeting, and your air and vapor retarder just goes up to that point of the height of the insulation on the roof. And there's a discontinuity there. What we've seen happen with there is, again, a bridge material to span across them, in between them, to basically shingle lap it, and then they both bond to that bridge material to help with that. That's one of the other reasons we kind of suggest divorcing it and having the insulation so you can get the full wrap too. Again, it can go through all different kinds of networks and channels into that roof. Again, in colder climates, that's going to likely cause condensation on the bottom side of the roof membrane and leak down through the roof, especially if the humidified building. If you're mechanically attached, this is an extreme condition, obviously. But the thing to note here is it's not just about this air that's magically floating up through the roof system, right? The wind is going to help suck it up in there. It's going to lift up the roof membrane and pull that air up into the roof system. So if this is happening in a cold environment, this really doesn't need much humidity in your building and can cause problems. This is a more common type of situation. This is not necessarily anything wrong. It's just to illustrate the pumping effect that you can get by the wind. And I will say, forget about the humidity for a second. Most of the materials that are underneath that roof membrane are probably not materials that you want inside your building, right? Like if we lined our walls with polyisocyanurate on the inside and just left them exposed, somebody would probably have a problem with that. Just chemicals, adhesives. If we just started smearing glue on the inside of our walls, we'd probably have a problem with that, the whole VOC thing. So when your air goes up into the roof by the wind being sucking it up, and then the wind goes away and it pushes it all back down into your building, I would suggest there's probably some contaminants going with it as well that we probably don't want exposure to. So if you really want to keep the air barrier, just tell them you don't want all those chemicals in your building. And that oftentimes will get the VE off the table. So lastly, don't forget about this other roof to wall connection here. We're not going to go through that, but the same mantra has to apply, the same methodology. How do we connect that low roof to the high roof? And now we're going to go a lot into windows, and specifically again, curtain walls. We're going to focus in on a jam detail, same idea, water, air, thermal, vapor. How do we line those up? I'm going to go even deeper just into this masonry wall type of detail with the typical curtain wall. We're going to spend a lot of time on the jam, and then we'll talk a little bit about other situations, because again, it's really about understanding the concept and what options are out there for us. So from a water tightness standpoint, again, 2 lines of defense. Connect the water resistant barrier with the primary seal of the curtain wall. Connect the rain screen seal of the curtain wall with the rain screen of the wall. There's other ways to enhance this. You can make it better, but at a bare minimum, try and accomplish this from a water tightness standpoint. From an air tightness standpoint, again, pretty straightforward. The air barrier connects to the primary seal, which is the airtight seal of the curtain wall. Again, back at the shoulder of the curtain wall. From a thermal standpoint, we love to line this stuff up as best we can. So line up the IGUs with the insulation that's in the wall as best you can. And it's relatively straightforward to do with curtain walls. It gets a little harder with storefronts and certainly a little harder with windows. And then vapor, again, same as the air tightness path. So we won't focus so much on that. How do we achieve that continuity? We're going to go through some materials and methods and get some risks and benefits associated with that. But right off the bat, we can say that we have a sealant joint that's connecting between the wall and the window. So this sealant joint that we're talking about right there, or if you watch it, you'll see that switch to a membrane. So we can glaze a membrane into that pocket there. So the two options that are very common, they both can work. They both have a lot of benefits to them, but each one of them has some of their own challenges, and that's what we'll walk through. So first and foremost, sequence of installations. I didn't ask, do we have contractors in this room? I assume we have a few, which is great. From a sequence of installation standpoint, the sealant joint transition is probably going to be one of the best from having flexibility of when people install what materials. I'm going to oversimplify it. I can practically build the entire wall. I can put in my curtain wall system, and then I can put my two sealant joints in between them. Now, I did oversimplify a little bit. There may be a little bit of dancing in there and ways to make that easier, but functionally, you could probably do this and do it reasonably well. From a membrane transition standpoint, it really starts to dictate a sequence one way or another and an orchestration of multiple trades working back and forth. So you got to build part of your wall and put the air and water barrier on it. You got to build part of the curtain wall. You got to put the membrane in between them. I would suggest then you got to build the rest of the curtain wall to kind of lock that down in place, and then build the rest of the wall around it. Finally, put the final seal, the rain screen seal in. So it forces this orchestration, which is a bulletproof detail. It really is, but it does challenge from a sequence standpoint. It doesn't necessarily have to be this sequence that I showed, but it is going to be some back and forth. There are other products out there, and I'll talk about this membrane transition 2 idea of leaving the tail flapping in the breeze. And I hope everybody's like saying, yeah, that doesn't work real well, because every time I see that, it gets beat up severely during construction. And then trying to put that into the glazing pocket miraculously around that tail without damaging it, even during the installation of the curtain wall, is virtually impossible. And where the impossibility is where the jam and the sill come together and the jam and the head come together. How do you keep that intact is very, very challenging when you're trying to leave this tail. So I think it's highly risky. If there's damages to that membrane, most of those manufacturers are going to say you got to cut out an area of the wall of about 6 square inches to repair it appropriately. So if you have to do that anyways, you're going to end up having to break that wall apart to get the repair done correctly. So I tend not to promote that one at all. There are some manufacturers that have some very specific products that can help address that in the field, but not necessarily as good as taking it right into the glazing pocket as you're going step by step by step. So let's talk about some of the materials here. Focusing in on the membrane that's wrapping the opening itself. What materials could that be? Lots of products out there. Fluid applied flashings that are out there, many of them STP based, some silicone based, and there are a few acrylics out there as well. And then self-adhered membranes, there's lots of options for that. Again, this is what the material is that wraps the opening. And we'll look at a few of these. This is a fluid applied material. And up close on that at a jam condition, you can see what looks to be a metal angle that's installed there. It's not a requirement, but if I put that metal angle on that rough opening, it gives me a high level of durability when that membrane wraps around it from the fluid applied. Many of our fluid applieds are quite thin, so they're not going to be real durable when it's getting beat up at a rough opening. They might be fine in the field of the wall, but if you want added extra protection, put that piece of sheet metal on it. It's not a requirement. Again, a lot of the manufacturers can go right on the raw edge of the jip, but what we see sometimes is when you just go on that raw edge of the jip, again, the world of construction is not always the nicest world. They can get beat up and they got to get repaired, or else you won't functionally get that transition the way you want it. Some of them are reinforced. Some of these fluid applieds are reinforced and they're still just using the field applied membranes, fluids to make that transition. Some are thicker. So some of them are actually going to have more body to them so that they can work with some of the maybe a little bit rougher substrates and nooks and crannies here and there. Nice part about this type of system, and there's lots of manufacturers out there for this type of system. This one happens to be a silicone. The nice part about the silicones and the STPEs is that in the curtain wall system, most of the internal seals are silicone as well. Most of the time, your transition sealant joint is going to be silicone. So if I can take another compatibility check mark off the list and have a silicone fluid applied membrane or an STP membrane, the odds of it being compatible are extremely high. And you have that all kind of one technology working for you. Again, acrylics are fine. All of these materials do need to watch out for horizontal surfaces though. Many of them don't like to have horizontal surfaces with our fluid applied materials. Not all, but many. And some of them switch over to a sheet applied product. Again, just from an absorption of water standpoint, some of the manufacturers don't like that occurring and want to switch. So it's a good intro into our rubberized asphalts. The biggest challenge we have with rubberized asphalts, again, nothing wrong with them, but there's definitely buildup of layers and seams on these materials. And then the sealant joint compatibility with that curtain wall. So will that stick to the facer of the peel and stick? There are sealants out there that are available that can be used, but they're going to be limited. You're not going to have this wide open selection of 20 different silicones that are going to work with these facers. So it's going to certainly have a limitation. The seams, I mentioned the seams. It might stick to the facer, but it may not stick to the seam. So a lot of times we'll end up buttering up the seams with silicone, put a Band-Aid over top of it so that when our perimeter seal comes across, we actually get a decent bond to it and don't have to worry about it. But those are areas that are oftentimes problematic for us. Overhead applications. Again, nothing wrong with the membrane. This can stick on an overhead situation, likely an installation problem that caused it to sag down, or water got in behind it and caused it to sag down. You don't tend to have these issues with fluid applied materials, and I will say most of our manufacturers have options for both. So it's not a manufacturer issue. It's just a personal preference. What kind of things do you want to try and deal with or not deal with in the field? Panelized construction, maybe a lot of this stuff can go away as well. This is a little hard to see here, but this is a self-adhered membrane, and you can see it kind of going down on an angle. You see that blue line highlighting it. What happened in this situation is the curtain wall anchor clamped down and pulled that membrane right off the wall. Trying to fix it after that happened is very, very challenging. With some of the fluid applied materials, when it clamps that down, it compresses down into the fluid applied material and goes kind of conforms around it versus pulling it off the wall by stretching the material itself. Substrate prep, we can't argue enough about this. I don't care if you're a peel and stick or a fluid applied shouldn't be installed over this stuff either. It's nice that they primed it. Again, it's got nothing to do with this manufacturer. Better substrates, you cannot do this with most materials and should not. Foil-faced materials, what we can use there, it's helped us tremendously with the compatibility issues that I mentioned, opens up the door for a lot more sealants, and that's one of the real big benefits, but it has some of the limitations of the typical self-adhered membrane. And you can see here where it's transitioning to that silicone, much less of a concern there from a compatibility issue. Other products that are coming onto the market in the recent past, self-adhered stainless steel, typically introduced as a flashing, and I tend to use it more as a transition membrane than I ever do as a flashing these days. It's great from a compatibility standpoint. It sticks to a lot of stuff, and a lot of stuff sticks to it. So when we're talking about trying to get these letters and compatibilities, a lot of the stuff is already in their back pocket. We just got to go ask for it. There's a few manufacturers of this stuff out there as well. It certainly works excellent, quite durable. It's very thin, but even from the thinness that it has, it's still quite tear resistant and puncture resistant. And then again, opens up the door from a compatibility standpoint rather wide with many materials. We'll go through these a little bit quicker. So I've kind of touched on some of the benefits or risks of every one of these. The fluid applied, it's seamless. That's one of the big benefits of this is you don't have to worry about that buildup of the seams. But you do have a cure time that you got to worry about. You can't just automatically go install the perimeter seal. You got to let that fluid applied flashing cure out first. Generally speaking, it's got great compatibility with all the materials that you might encounter, but there is that possible water absorption that you got to watch out for. Self-adhered, I mentioned it, the seams, the buildup of layers, especially, it can start eating away at how big that gap is between the curtain wall and the rough opening. And then again, depending on the facer, what is the compatibility of the sealant joints themselves? Moving into how we glaze into this pocket. So what are some of the material options for this? And we got them all listed there. We got, again, the self-adhered rubberized asphalts. It's an option. Self-adhered stainless is an option. Sheet metal could be an option. And then pre-cured silicone is also an option. They're all options, but they also have some issues with every one of them. Right off the bat, rubberized asphalts are not going to be able to bridge that gap between the window and the wall very far. 1/4 inch, 3/8 of an inch, generally the top. They also, when you're glazing it in the pocket, the rubberized asphalt's not going to stick to the silicones that are inside that curtain wall. So you're going to automatically have challenges with that when you glaze it into the pocket. Self-adhered stainless, similar issue. It's typically butyl back, so it may not want to stick to some of those silicones that are inside the curtain wall. But from a span limits, they don't necessarily have limits, but there's a reality behind the limit. They require somebody pushing on the seams. If you have a big gap that you're trying to span and you're pushing on a seam, you need compression there. If you're not getting that compression, you're not getting a good bond at our seams. So you got to watch out for the reality of some of the span limits with that. Sheet metal can be great, can be extremely durable, but these curtain walls generally are big, right? Curtain walls need to take movement. Sheet metal doesn't take movement. So if it's a small opening, you could potentially basically try and turn your curtain wall into a flanged window, but you got to figure out how you're going to take the movement if you want to go with that approach, which oftentimes leads us to, and you guys are probably familiar with this, certainly be on the West Coast, is pre-cured silicone, bridging that gap. Again, it's silicone to silicone. The silicone will bond to most of our air and water barriers on the market as well. Many of the manufacturers has it as an accessory. And the big downside to that is the lapse. So when you're putting any of these materials into our glazing pocket, you're building up lapse at corners and at seams. That has challenges with the glazing pocket compression. Some curtain wall manufacturers are absolutely against it. As soon as you do this, they didn't test it that way. And if there's ever a problem, it's your problem, not their problem. So you really, and from a specification standpoint, you need to make sure that the curtain walls that you're specifying will actually support the use of this type of application, because not all of them will. So the other kind of weird thing about these pre-cured silicones, and I'll show you a little bit better photo here, they rely on a bed seal, so it's not an adhesive bond where you're trying to push on it. You gotta bed it in sealant and let it cure. Not the prettiest stuff in the world, if anybody's seen it. We like to terminate the top edge with more sealant, just to make sure that the bed seal, if there's any voids in it, because bed seals are very challenging to trust. So we want to terminate that top edge as well to make sure that there's no issues. And quite frankly, all the seams should be terminated. We like to use translucent materials so you can see through and actually hopefully see the bed seal. Black sealant, translucent material, the best shot you're going to get. Just a few examples of some of the complexities you can handle with pre-cured silicone though. And the amount of flexibility it has, the amount of stretch that it can have. You can build up a lot of unique conditions in the field. Again, not the prettiest stuff, which takes a good eye to see if there's a problem because it is a little bit challenging from the installation standpoint. You can get pre-manufactured inside-outside corners, so that will help with some of these transitions. And I strongly encourage their use so you're not trying to fold origami with silicone. It's very challenging and almost impossible to do. All right. Last one there was self-adhered rubberized asphalts glazing in the pocket. Very limited application. I would tend to avoid it whenever possible. And then, so let's wrap this section of it up with the sealant joint versus membrane. The big benefit of the sealant joints, just like installation, future repairs can be handled relatively easily with the sealant joint. You don't have to tear apart the entire wall typically. They're very compatible with a lot of the materials. Sequence of installation is good, but they do have their limits. If that curtain wall gets pushed outboard and not aligned with the air and water barrier, that sealant joint gets nearly impossible to install. So you really got to watch out for the alignment of that shoulder of the curtain wall with the wall itself. Sealant joint tolerance, if it gets too tight, so sealants don't work. They got to be able to move. So you need some body, but you don't want too much body. If they get too big, they don't work. So if your rough opening's a little bit out of alignment there and a little bit out of tolerance, could be a problem from a sealant joint standpoint. And then if you're sealing to a sheet membrane, sometimes those compatibility issues come up as well. Benefits of the membrane transition. Again, bulletproof detail. You don't have to worry about some of the compatibility issues with the sealant joint to the membrane. Now you got to worry about it with what's going on inside the glazing pocket. Good news is we can span narrow gaps, but some of them can't span big gaps, depending on what product you're using. More limitations, to me, the big issues are the seams and trying to do that three-dimensional origami with sheet applied products. So won't go through all those lists, stuff we've already touched on.
Wouldn't there also
It's typically, well, again, depending on the product, but let's say it's pre-cured silicone. It's bed sealed to the curtain wall, and then the curtain wall mechanically locks it in. Some people like to put a fillet bead inside the curtain wall to terminate the edge. But if you're talking about behind it, you don't need one behind it. And I will say, especially if it's pre-cured silicone, because it can span across it. It's functioning as your air and water barrier for you. You don't need another seal behind it. You can. I've seen people do that. I'd rather have the other seal in front of it. Lastly, again, some manufacturers allow this. Just remember, check to make sure they actually allow going into the pocket, because many don't. Moving on into the other applications. Basically, everything we just said about the last 20 minutes about the jam apply to the head and the sill. We architects like to articulate our buildings in and out all over the place, right? Keep the plane of the air and water barrier hopefully in the same spot, makes everybody's life a lot easier. Move the cladding in and out. But try and keep that alignment with the shoulder of the curtain wall with the air and water barrier. It makes for life to be much easier. I'm going to talk about a detail that I don't love. And again, curtain wall specific, taking a metal flashing underneath the curtain wall. There's a lot of challenges with this, and it really doesn't add a lot of value. So if I highlight that with the blue line, what's the #1 purpose of a flashing? Shed water. And I'm going to stretch that to collect water. What else for flashings? Bridge gaps. I guess I'll just jump into the shed part. Collect it and then get it away, right? Transport it. So if those are my main things, and then bridging the gap, which it can do as well, and we want it to do that. If my curtain wall has failed 2 lines of sealant or 2 lines of defense on the curtain wall system itself already, and I collect it in this flashing that's underneath the curtain wall, how do I get the water out? What's that? Slope it. What else I do? I also have that sealant joint that's at the primary line of air and water tightness for my curtain wall. I would have to poke holes in it. Manufacturers don't like poking holes in the keyword primary line of air and water tightness. So if the purpose of the flashing is to catch and release the water, I now have to poke holes in my primary air tightness line. So the other issue is we're not really getting an effective air seal back there where it wants to be, because if you remember, the vertical and horizontal mullions aren't sealed to each other typically. That's not a standard for the manufacturer. So I'm creating an air path by doing this type of application on the top side of the flashing. And it goes right through those mullions and right out the weep that we put into the primary air seal to drain that water, if that's what we wanted to do with that flashing. So that's one of the issues with it. Another issue is from a thermal standpoint, by introducing that flashing. Again, if condensation is of an issue, same window, same wall, just putting that flashing in 2 different spots. The one on the left is all the way back, the way we just showed it. The one on the right is actually tucking it up into the glazing pocket. There's a 10-degree surface temperature difference. Nothing else has changed. It's acting as a significant thermal bridge. And again, on certain climates and humidified buildings, that could be a major issue. Other thing what we don't like doing with flashings is poking holes in them, right? I mean, that's 101 for flashing. Stop poking holes in them. #1 way of attaching this type of curtain wall is to anchor down through the substrate right directly underneath of it. So you're going to ultimately be poking holes in that flashing material. So we could try and make the argument that, well, the flashing isn't really functioning as a flashing once it's under the curtain wall. We're just using it to anchor that flashing a way to mount it. But there's other issues with that as well. We got a lot of splice joints in that flashing material. We have a bed seal for that flashing material. The bed seals are inherently challenging because I can't even see them. So I don't know how well they are from an air tightness standpoint, because now the flashing has to become a part of the air barrier system. The seams and all that flashing need to be sealed air and watertight. And they may be sealed, but they're sealed back there a ways. And this creates a little wormhole at every splice joint. And forget about the little bit of air leakage that goes through. I'm more concerned about the water leakage that goes through there. And we see it often. This is a little bit out of order. The one problem is slope it, right? So pitch it up. Well, these people pitched it up and blew my air seal that was underneath of it, if it's ever there in the first place. There's a situation with substrate prep. You watch the orange string that I found laying around. It goes all the way out to the outside underneath that flashing. And if you look around on the bottom side, the curb had all kinds of holes and defects and everything else. So there's all kinds of problems with the bed seal that are concealed. You can't see them. It's really hard to QA, QC this type of application. Those seams that we talked about where it could be a water leak, that's the other side of that seam. This was during a test, and it looks like just a tiny little drop of water, no big deal. But when we do these types of tests, that tiny little drop of water is a continuous flow. And this is when we knew we were going to be testing this. And it's not just a tiny little drop of water. Over just a few minutes, it turns into a significant amount of water. Granted, we can say that's during a test. Is it ever going to happen in real life? I don't care. It's the test. It's the test that's supposed to pass. So that's probably more on a storefront. So the question is, what do I think about the sills that come from the manufacturer? From a storefront standpoint, 100%. Use them. Don't put another flashing underneath it, because that is the flashing, right? It's an integrated, it's designed. Now you need to continue to bridge the gap outboard of it, which another metal flashing needs to be used to do that. We do have another presentation about that exact issue that we could talk about. But for curtain walls, you don't typically have that integrated flashing. Oh, you just ruined my surprise, but go ahead. Yep. Yep.
A lot of the manufacturers don't allow you to apply sealant at the fastener.
Yep.
So then you have reverse slope water.
And what we've seen is those anchors. So the comment was those anchors can cause reverse slope because it's compressing it down. And the manufacturers don't want you sealing those anchors. And what I've seen is you have them typically every 3 to 5 feet, right? Is where you're going to have those anchors. Then it causes the flashing to bow in between, which again breaks that bed seal that's hopefully underneath. So we can fix it. This is the ugly fix, I guess, from the top side. That's the pretty fix. But again, this is the top side. What's happening underneath the path? It may not be a water leak, but it could be a continuous air leak all the way across the sill flashing. So what we tend to do, again, seal directly to the air and water barrier, to the shoulder of the mullion. Let the flashing be the gap filler that it needs to be. It can still shed water on the rain screen, but take it and get it out from underneath that curtain wall. It just introduces too many problems for us. Head system as well. We're going to go rather quickly because we just got a few minutes left. Same idea. Keep the lines of performance aligned from jam to head to sill. Same kind of concept. This happens to be at a brick wall where we have a big lintel. And here's our 2 lines of sealant in reality. Again, not always the prettiest stuff, but it does work when it's applied right and well. Here's where we can take that lintel and break it off from a thermal standpoint. So we get better continuity of our thermal insulation, which is good, but it does have its own kind of issues to deal with. The mock-up conversation that you had, every one of these clips, how do you detail around every one of those clips? A lot of these clips are homemade. Some are manufactured, but how are we detailing around it when you got a homemade type of situation? These manufacturers in the back don't have a detail for every way we can possibly come up with a thermal break and a steel lintel. So the point of that, how do we detail around that? Mock it up, right? We have to test this out, whether it's off the building or on the building. You'll discover stuff, you'll find stuff out. We found out that there was a hole right behind that for the bolt access, which was a leak in the air barrier every time that needed to be sealed. And that same thermal performance, again, whether we have that lintel all the way back or if we're thermally breaking it off, makes a significant difference in the thermal performance of the system. We didn't change anything else on the wall, didn't change anything else on that curtain wall in those models. And it's, again, nearly a 10-degree surface temperature difference because of the way we designed that lintel. So if energy and thermal performance, carbon reduction, all these things are important, these are the types of details you want to try and head towards. And head away from this. No pun intended with the head. Problems galore. Thermal bridging primarily, continuity of interfacing materials, transition materials lacking. Flush mounted windows, pull them back anyways. Windows leak. We all know windows leak. The best intentions, they will still leak. If I can shed the water and never have it get water on it or less water on it, it's going to be better altogether. And again, from a thermal performance standpoint, pushing that window out, not aligned with the thermal barrier of the wall itself, is going to be a significant difference in performance. Same wall, same window, just the alignment is not being captured. And this stuff doesn't get captured in our energy models. So we need to be honest about it and try and make it better. So the last thing I'll go real quickly through, and this is for us architects. we need to do more 3D detailing. And it doesn't have to be extensive. We don't have to 3D detail everything. And it doesn't have to be super detailed either. It can be conceptual level like I showed today. Here's one example where we did it. And complex little interface of lots of different roofs, walls, and windows all coming together at one spot. And we kind of did a sequence drawing, but it wasn't, you must build it this way. It was, here's a concept of how you, if we peel back the onion, if you will, and if we just walk through it, here's the structure. And then as we start putting more substrate boards onto that structure that can take our air barriers. Here's our air barrier for the wall and some more substrate for the curtain wall to catch the next piece. And this is where I lost the VE battle. Now I don't have a dedicated air barrier on my roof. So we have a roof membrane. So how are we going to make that airtight to the curtain wall? How are we going to make that airtight to the wall? Then we add our flashings. We strip in that flashing to make it more watertight. And then finally install our claddings and counter flashings. So this is not a dictate, this is the way you shall build it. This is if I take apart those layers, this is what I expect to see inside those layers. So I think what we did with this project, we did that one sheet, that one set of sequencing, and it applied to 6 or 7 places around that building. So we didn't have to do it a lot of times, and it saved us tons of time in RFIs and construction related issues down the road. So we have better tools now as architects. We got all kinds of different 3D modeling software. We need to be using more of it because the manufacturers have some great standard details that are 3-dimensional. They're not going to have, that's going to address every one of these conditions. Lastly, related to 3D detailing, that was the easy one. This is where we had 1, 2, 3, 4 curtain walls coming together, 2 rain screen walls, 2 different soffits, and all of that is happening at an expansion joint. So how do you get continuity of all those layers that we just talked about? And how do you draw that as an architect? You're not going to get that with, it's going to take 40 sections to figure that out, and it still won't be figured out. So we got to find a way to use our tools wisely again. So we got brought in and we basically made SketchUp and Revit models and stripped down the structure again. Just not that it was going to be built this way, but just peeling back the layers of the onion so we can see where do the parts and pieces have to go. So we built that sequence of putting back the layers. Okay, we need substrate boards here and there to have a surface for our air barriers. Then we can install our air barrier materials where they apply. Then the next line is you're seeing all the expansion joint material coming through, and rather complex, but somebody had to show the path of that expansion joint. And then you can put back the other layers of the curtain wall. Again, some of this was unitized, so it was just stripping it back for illustration purposes. Then installing the soffits, finishing up with the rest of the system, install the cladding materials and glaze the rest of the curtain wall systems. And there's kind of a in construction photo of it. And the final photo of it is that on this tiny, tiny little spot on the building right there. But the reality is that same tiny little spot, again, on this project, there was 16 of them the exact same way. So that one set of sequence details, they were able to apply that all the way across the building in various types of conditions. The reality is we had a half-hour meeting with all the subs in a trailer, walked them through that sequence. They all walked out saying, okay, we get it now. So a lot of effort put forward to do the detailing, but it saved tons of time and tons of problems that might occur during construction. None of them blinked. It's been a few years, so I hope it's. Well, anyways, thank you guys for having me, for having us. Definitely, I'd love to take some questions if you guys have any. I know it's a lot of information to absorb and tons of ideas and thoughts. Again, nothing wrong with the materials. There's lots of different options. Some of it is going to be personal preference by you versus me versus other people. And again, as long as we're just doing it appropriately, we can make them all work. So, any other questions? I know you guys are hungry. So am I. I'm from Detroit. All right, well, I'll be around. So if there's anything else, again, thank you for your patience and your attention. I appreciate it, and look forward to seeing you this afternoon.
Thanks, Andrew. That's much appreciated. We do have lunches in the hall. There are wraps and sandwiches and salads and vegetarian and gluten-free options. So please help yourselves. And we will reconvene at about 12:45 with another presentation by Laverne. Thanks, everybody.
Yes, sir.
We want to take it into sidebar. Like we do a lot of testing, and where we generally see failures is curve walls.